close enough to 1 o'clock that we should go ahead and begin. So good afternoon to all of you. Hopefully you're enjoying our rainy week, or now month, that doesn't want to go away. See, we got 4 inches of rain yesterday. Maybe it'll be 8 inches today and tomorrow, huh? If we're going to get flooded out, we might as well do it right. Well, for now, I'm not going to worry about the weather. First of all, we're starting a new week, so I guess that means I need to give you more homework. That's always fun. So let's see. Mostly it'll be from chapter 4. I'm actually going to assign a couple of chapter 3 problems that I feel really are more applicable to the chapter 4 material than the chapter 3 material. But anyway, this is all part of your 4th homework set. So this will be the work for the entire week, due next Wednesday as usual. By the way, I've just put them in this order because that's the order that, kind of naturally follows the material. If you feel like solving chapter 3 problems first, that's okay. It doesn't matter at all. Okay, so there's your homework set number 4. Let me also remind you that your first midterm exam is 2 weeks from today, on the 6th of February. So not something to really worry about, but you don't want to let yourself fall behind. The material on the first midterm really could cover anything through section 4.2, which is pretty much through this entire week. All right, so let's just get back to where we were last time. Remember, we're beginning chapter 4 now. We're starting to talk about, the use of the first law, although we haven't really quite gotten to that yet. Specifically, we've been talking about a particular type of work that we call boundary work. And it should be noted that whenever we have a system that undergoes a process where the volume changes, there will be boundary work. I mean, boundary work is really shorthand for moving boundary work. If the boundary is changing its position, therefore the volume is changing, and therefore we have to have some work. And the basic equation for boundary work was really just the integral of PdV between some initial point 1 and some final point 2. Now, please note we're talking specifically about closed systems here. So 1 and 2, in the context of this type of problem, would represent the initial and the final state. So 1 is the initial state, 2 is the final state. And if we want to figure out how much work is done based on the moving boundary, we just integrate this equation. Now, some relationships are pretty simple. If we have a constant pressure process, then this equation becomes pressure times change in volume. If we have a constant volume process, well, then that just becomes 0. There's a whole category of problems where P times V raised to a power n is equal to a constant. And whenever we have this type of relationship between pressure and volume, then we just call this a polytropic process. So in order to calculate the boundary work for a polytropic process, we basically just have to plug this equation into the one above and go through the mathematics. And I didn't actually go through the derivation last time, but I did give you the final equations. There'll be a different equation depending upon whether n equals 1 or n equals anything else. But nonetheless, the book goes through the complete derivation, and you can look at the derivation there. I'm not going to rewrite those equations. Nonetheless, polytropic processes are very, very common. You might note that this PV to the n equals a constant basically gives us this whole family of curves with different inflection points and different slopes on the different curves. So pretty much any process between some initial point 1 and final point 2 probably can be represented by a polytropic process. In fact, that's generally what we find. Almost any process is polytropic given the proper value of n and the proper value of c. Now, you will be told that it's a polytropic process. You're not going to just have to guess whether it's polytropic or not. There is certainly one exception, and that'll be the first example problem I'm going to give you, which I'll just start right now. So any questions just in general? Again, this is really review from last time. All right, so let's look at an example problem. And even though I'm not going to tell you it's a polytropic process, you'll be able to see right away that it is a polytropic process. So let's say that we're given O2 gas, and initially the pressure is 20 psia, and the temperature is 120 degrees F. And I'll stay whose mass is 0.1 pounds mass. Okay. And now we're told that this gas is, and I'm going to use the word isothermal for the first time. So this gas is isothermally compressed until the pressure reaches 65 psia. Okay. And what we want to do then is we want to find out how much work is done. Find the work done. Okay, so this is a pretty simple example problem. It may not be clear yet why it's a simple example problem, but we'll get to that shortly. All right. So the first thing we have to think about is, well, how do we even begin to approach this problem? We know that if the pressure and volume change relative to one another, then it should be some kind of polytropic process. But unless we know the value of n, we really can't solve for the work, because the equations, as we've seen, are not only a functions of the initial and final pressure and volume, but also a function of this polytropic exponent that we call n. So I suppose we have to ask ourselves, well, maybe this process really is polytropic, and we just don't know it yet. And the key actually lies in this word here, isothermally compressed. Okay. Now, first of all, what does isothermal mean? It means constant temperature, right? So whenever you have a process that's an isothermal process, there's no change in temperature. So basically T1 is equal to T2, which is the same 120 degrees Fahrenheit. We could actually convert this into Rankine. We'll need it eventually. We'll just add our 459.67. So we end up with, what, 579.67 degrees Rankine. So isothermal compression means constant temperature compression. All right, so we know that the initial and the final temperatures are the same. Now, don't we also know that these are all closed system problems, right? We know we have a certain mass. So T is equal to a constant. The mass is also equal to a constant. And then can't we also say that R, which is our gas constant, is always equal to constant? So why is this important to me? Does this really matter? Well, it does, right? Because if it's an ideal gas, and we'll actually check this in just a moment, then we would know that PV equals MRT. Right? For any ideal gas, PV equals MRT. So if we can determine that this is an ideal gas, which we will do shortly, then this is one of the appropriate ideal gas equation of states. But if M is a constant and R is a constant and T are all constants, then this equals a constant. And we might as well just call that constant C. And don't we also know that V is just the same thing as V to the first power? So can't we just write this as P times V to the first power is equal to a constant? So isn't this one of those polytropic relationships? Isn't this of the form? Yeah, so isn't this of the form P times V to the nth power is equal to a constant with n equal to 1? Sure is, right? So if this is an ideal gas, then it turns out that it's also undergoing a polytropic process with n equal to 1. So I guess the only question is it really an ideal gas? And we have to say, well, it's an ideal gas if, and there's a couple of tests we can make. One of the tests is that the reduced temperature, as we called it, which is equal to the actual temperature of the critical point temperature, is greater than 2. This is just that test that I gave you last time. So the question now becomes, is it greater than 2? Well, we know the temperature is 579.67. We have to do this in Rankine. We can go into table A1 and go to oxygen, and we'll find what the critical point is. So if maybe now would be a good time to, well, you pick. Anyway, let me go to table A1 here. That should pop up on the side here shortly. Yep, so there's table A1. Here's oxygen. The critical point properties are these last three columns over here, the first being temperature. So the critical point temperature is 154.8. Oh, you know what? I'm in the wrong units. So yes, thank you. We've got to go to A1E, not A1, right? All right, so that's better. It's always nice to use the right numbers. Okay, so, whoops, here we go. So here's A1E. Yes, this is correct now. So down to oxygen, 278.6. So let me just change this, A1E. So 270, what did I say, 278.6. And this actually equals 2.08. So it's greater than 2. Therefore, it's an ideal gas. And it's polytropic with n equal to 1. Right? Now, I will tell you that many times you will find that processes involving ideal gases are indeed polytropic processes. That doesn't necessarily mean that n is always going to equal 1. This was a special case, right? This was a special case of an ideal gas that was also undergoing a constant temperature process. It turns out that any ideal gas undergoing a constant temperature process is a polytropic process with n equal to 1. Well, nonetheless, now that we know that it's polytropic, the boundary work is therefore just going to be P1 V1 times the natural log of V2 over V1. This was the equation that was presented to you last time. So all we really need to do now is find the values of P1, and that's already given to us. So really all we need is to find V1 and V2. Well, it's not so hard to do. So let's just proceed with this problem then. First of all, it's an ideal gas. So PV equals MRT, or if you will, P1 V1 equals MRT1. So I can actually substitute that right in above. Also, we want to note that if I divide out the pressure, I get V1 equals MRT1 over P1. Similarly, I can do the same thing at point 2. I can say P2 V2 equals MRT2. I mean, it's still an ideal gas, so that equation still applies. And therefore, V2 is MRT2 over P2. So now you can see I can plug both of those equations for volume directly back in above, and I get the following. So I get that the boundary work is MRT1 times the natural log. And let's say if we plug all these terms in, the mass is constant, so it's going to cancel out. The R is always a constant, so it's going to cancel out. The temperature happens to be a constant because it's a constant temperature process. So basically everything cancels out except for the pressure terms. So basically I should just say plug into above in order to get, and we get this equation, right? Again, everything else is canceled. If you want, you can write in the MRT1 over P1 in the denominator, the MRT2 over P2 in the numerator. Again, cancel everything out, rearrange, and this is what you end up with. And now we can solve the problem, right? Because everything is known. It's just a matter of plugging in numbers. So we have 0.1 pounds mass. We do have to go into table A1E one more time and look up the value of the gas constant. We can use either column of data. Although in this particular problem, we don't have any pressure data that doesn't just get canceled. So we don't need to worry about the pressure units of PSIA. I think it'd be best just to use the first column of data with the BTUs per pound per degree units, and that's going to give me the appropriate units. I'll end up with BTUs, which is what I want. So the number is 0.06206, and this is going to be BTUs per pound mass per degree R. The temperature T1 we already know, that was 579.67 R, and then the natural log of this pressure ratio. The pressure of 0.1 we were given in the problem statement as 20, and then 65 is a pressure of 2. So we have 20 PSIA over 65 PSIA. You do have to use the absolute pressure units. You don't want to use PSIG, or it doesn't work properly. The ratio is not going to be quite right. Is there a question?
Why are we using BTU units rather than the PSIA ones?
Well, the only pressure units we have within this problem are right here in these two pressure terms that are just going to cancel out. The units that we want to end up with are going to be energy units in BTUs, which is the standard unit in the British system. So this equation, the R term, is the only place where the energy units are going to come back into the problem. Now, yeah, I could use the other number. I could use the one with the units of PSIA foot cubed, pound per degree R, but then we end up with the work, and the units will be PSIA foot cubed, which are just rather odd units. So I would always pick the units that seem to make the most sense, and here it's the BTUs. Anyway, it's just a matter now of going through the mathematics. I'll let you plug and chug, and we end up with minus 4.240 BTUs. So that's the amount of boundary work, and that's the end of this particular problem. So just a pretty simple problem. The math was simple, right? If you didn't recognize that an ideal gas undergoing a constant temperature process is also polytropic with n equal to 1, there's no way you could have done this problem. But if you recognize that, that's really the only way you can solve this problem. So again, this is just an example. Let's look at the minus sign. Does the minus sign make sense to us? We're starting with some gas, and we're supposedly compressing it, right? We're compressing it. Presumably, it occupies a smaller volume as the pressure rises, right? So it just makes good physical sense that work is being done to the system, not by the system, right? And for work being done to the system is considered negative. The negative makes sense. If you go through the problem and you end up with a positive amount of work, then that says work is being done by the system to its surroundings, which kind of implies that the volume is increasing, which should result in a pressure drop. Not the case here. So this is what's happening. The sign makes sense. You can put work by the system, and I'm sorry, I wrote that wrong even though I said it right. Negative means that work is being done to the system, right? Positive is by the system. So I spent all that time talking about how this is to the system, and then I wrote by. No, work is being done to the system because of the negative sign. Remember that heat transfer is different, right? If you had a negative heat transfer, it's heat transferred away from the system. With work, negative work is work done to the system. Yes?
Earlier in this problem, you assumed that V equals V1 to the 1 power, and that's how you reduce those polytropic.
Right. Once we recognize that V is just another way of writing V to the first power, then you'll see that it's of the proper form. P times V to any exponent, and in this case n equals 1 is equal to a constant.
So what if, how would you know to do this if it wasn't equal to 1?
You would have to be given in the problem statement that it was a polytropic process, you would take a polytropic exponent. In fact, I'll do another example problem now, which will be kind of another typical problem. This problem is unique, but it's not uncommon. If you have a well-insulated container that contains a gas that undergoes a process, the fact that it's well-insulated means that there's no heat transfer. It's also very possible the temperature could remain constant, so these are not uncommon types of problems. But still, it's a unique problem. Let's look at a more generic problem, which might make this more understandable. Okay, so again, any questions on this one? All right, so let's just look at another example right away. We're not even going to identify what the substance is. Let's just say that we have some closed system. So we have a closed system. Where we know the following. Okay, so let's assume that we start with a volume of 1 cubic meter, and let's say that we end with a volume of 1.5 cubic meters, and we end with a pressure of 0.5 megapascals. Okay, so we have a closed system where we have this information. The substance has undergone a polytropic process with N equal to 1.4. And what we want to find is the amount of work that's done. Okay. Now, this one, we're told that there's a polytropic process. We're actually given the final state. We're not given the initial state, right? We do know one property at the initial state, and that's its volume, but we don't know any other property at the initial state. All we know is that there's some polytropic process that's taken place, and the polytropic exponent is 1.4. Now, you're told that it's polytropic. You're given the polytropic exponent. Even though I haven't used the word boundary work, this is clearly a boundary work problem, right? I mean, that's the only context that we've really even covered these polytropic processes, is as some form of boundary work. So we know that the boundary work is going to be, well, in this case, n does not equal 1, so it's going to be of the form P2V2 minus P1V1 over 1 minus n. Now, that looks pretty good. We are given P2 and V2. We're given V1. We know n. If we can somehow find P1, then we should be able to find the boundary work. Now, how do we know what that initial pressure is? Is there something we're missing here? Do we have some other equation we might be able to use? Well, remember that if it's polytropic, then that means P times V to some power is equal to a constant. So can't we just say, well, at point 1, can't we just say P1 times V1 to the n is equal to that constant? Can we say that at point 2, P2 times V2 to the nth power is the same constant? Right? I mean, it's constant. It's a polytropic process where at any point, point 1 and point 2, P times V to the n is equal to a constant. So therefore, P1 V1 to the n equals P2 V2 to the n. We know everything in here except for P1. So we solve for P1. So we get P1 equals P2 times V2 over V1 to the n. And now we just plug in the numbers that we have. P2 is 0.5 megapascal. V2 over V1 is 1.5 over 1 raised to the 1.4 power. So if we go through the mathematics, we get 0.882 megapascal. All right, so now we know the initial pressure. Now we just take that initial pressure and plug it in to the boundary work equation above. And we get the following. So again, it's just a matter of plugging in the numbers. All right, so P2, we have 0.5 megapascal times V2, 1.5 cubic meters, minus P1, So 0.882 megapascal times 1 cubic meter, and then over 1 minus 1.4. We go through the mathematics, and the units are going to end up to be a little bit odd. We get 0.330 megapascal meters cubed. Okay, those would be the units that we would end up with. And you may look at that and say, well, that's hardly pressure units. I'm sorry, it's hardly work units. But it kind of is, right? Let's just go through some conversions. I mean, we know there's 1,000 kilopascals per megapascal. So basically, this is 330 kilopascal cubic meters. And then we'll do the same thing that we actually did in one of our examples last time. Kilonewton per square meter is a kilopascal. A kilojoule is a kilonewton meter. Kilonewtons cancels, kilopascals cancels, all the meters cancel, and we end up with 330 kilojoules. Pen's about to die. All right, so there's just an example problem. Another example problem of a polytropic process. Are there any questions on this particular problem? Yeah. Well, I mean, yeah, but then the people on that side are going to have the same issues. I mean, maybe what we need to do is just kind of turn it a little bit or something. I don't know what to suggest because I don't want the wires to come unplugged.
Or on the backwards too.
Say that again?
On the backboard is up too. Back.
Well, yeah, I mean, the one is back there too, but I don't know if that helps you guys. It's just so I can see what's up on the board. Things will get better. I just replaced the pen, so it's a little bit dim. Yes?
So in the first example, did we just assume that n equals 1 because we're told it's isothermal? And then on the second one, because we're given n?
Right, although on the first problem, it wasn't just because it was isothermal, it also had to be an ideal gas, right? Because PV had to equal MRT, which turned out to be a constant because T was a constant. So it was an isothermal process, and it was an ideal gas process, and that is what allows us to show that P times V to the power of 1 was equal to a constant. So it's kind of a little bit of both. Now again, that's unique. Not a lot of isothermal ideal gas problems, but there's plenty of just generic polytropic processes like this one. Yeah.
Is there a situation where we'd have to find n by ourselves, or if we tell if it's polytropic and they give it to
Well,
us?
sometimes. I mean, for instance, if I had given you this problem, but what if I had given you initial and final pressure instead of the final pressure and the polytropic exponent? Yeah, so in that case, you could go through this equation, and that would give you one equation in terms of the unknown work and the polytropic exponent. And then you'd also have to look at this other equation, which would also be in terms of an unknown polytropic exponent, but you'd have the pressure. So yeah, you would just solve this equation for n and then plug it in back above to get the work. In the example problem as I've given you, you plug everything in for your unknown P1, and then plug that into the work equation to find the work. So it would be a very similar problem, but yeah, those exist. The key is that you have to remember that P1V1 to the n equals P2V2 to the n. This is a very important equation, although it's very short. If you don't remember that equation, then you have no way to find the polytropic exponent. So that equation, along with the boundary work equation, are the ones that you're going to generally need in all of the problems of this type. Okay. Anything else? Okay. What if we had a sealed rigid vessel? Oh, I think I gave you this one last time. We know if it's a rigid vessel, there's no volume change, so there's no work, right? Think about those kind of things. All right, so now we're going to actually move on. We're done talking in general about work. We're certainly not done using work. We're going to use it in pretty much all our problems for the next 2 months. But let's now begin in earnest about this discussion of energy balances for closed systems. So, energy balance for a closed system. Now, this is essentially the title that I put on the lecture last time, but we didn't look at the energy balance right away. We just right away went in and started to look at work and boundary work and all of that. Now we're going to actually look at the energy balance equation, and we've actually seen aspects to this equation already. We saw earlier, and this would have been a week or so ago, that the difference between the energy that flows into the system and the energy that flows out of the system is simply the change in energy of the system, which we can just call E2 minus E1, where 2 represents the final state and 1 represents the initial state. Okay, so this is something that we've already seen, and I think we understand. I'm just going to call it A, okay, to just give it an equation number. Now, we also know, and this is something we've seen previously, that the difference between the energy in and the energy out is equal to the difference between the different types of energy that can flow in or flow out. So for instance, this was equal to Q in minus Q out plus work in minus work out. Q, of course, is heat, right? So plus work in minus work out, and then plus any energy that flows in minus any energy that flows out. Okay, so this is something that we also hopefully remember from a week or so ago, and I'm just going to call this equation B for the time being. Also, perhaps we remember that the difference between the initial and the final energy is not just equal to the change in the heat in or work in or energy that flows in and out. It's also equal to the change in the internal energy plus kinetic energy plus potential energy, right? So also, we could just write that E2 minus E1 is just going to equal the change in internal energy plus the change in kinetic plus the change in potential energies, or if you will, this is just U2 minus U1, then plus 1/2 m V2 squared minus V1 squared, and then mg Z2 minus Z1. Okay, so this is something that we also saw previously, and I think I'll just call this one equation C. So these are all relationships we already have talked about, right? The difference between the energy that goes in and out, whether it's heat, work, or whether it flows in or out, is equal to the change in the energy of the system, which is either internal energy or kinetic energy or potential energy. So what I'll do now is I'll just plug B and C into A. And in plugging B and C into A, we would get the following. Now, let me just note, before I actually do the plug away, nothing is flowing in, right? E flow is just 0. This is a closed system. We're still talking about closed systems, so that there's no masses flowing in or out. So the energy in that flows, the energy out that flows, these are both equal to 0. Also, we would note that one alternate way of writing the change in internal energy is just the mass times the change in the specific internal energy. So we're going to plug B and C into equation A above, and at the same time we're going to make these substitutions. And as we do all of this, we basically get the following. We get m times lowercase u2 minus u1 plus 1/2 m v2 squared minus v1 squared plus mg z2 minus z1. Okay. So this is then going to equal q in minus q out, and then plus work in minus work out. Now again, the energy flow terms canceled out. So this is the equation that I have now. Let's just rearrange this. Okay. And as we rearrange this, well, basically we get the following. So I'm going to move the heat transfer terms over to the left-hand side, which is something that we typically do, and then leave the other terms over on the right-hand side. Okay. So I have all these terms, and then I also have the work. So this is going to be work out minus work in. Okay, the order of the work terms changes. Essentially what I've really done is I've moved the work term over to the left-hand side, and then put everything from the left over to the right, everything from the right over onto the left. So the signs are all correct here. So we get this equation. I'm going to call this one equation D. And then lastly, I want to note our sign convention. So based on our sign convention, we remember that the heat transfer in this process, and we are going from point 1 to point 2, would be written as Q12. And we know that this is a positive term if heat is added and negative if heat is rejected. So Q12 is really just going to be Q in minus Q out. Okay, well, we don't always just have a single heat transfer term. We looked at a couple example problems last week, where maybe we have some heat being added because of the lights and because of the TV, maybe some leaking in through the windows or whatever. So we might have multiple terms, but the Q1 term is positive as long as Q in is positive. If we have any heat rejected, then the magnitude of the heat output is going to have the negative sign associated with it. So this is consistent with our sign convention. And similarly, the work that's done as we go from some initial to final point, this is going to be the opposite now, right? This is going to be work out minus work in. The work out of the system is considered positive, and work into the system is considered a negative. So what we will do is, based on the sign convention, now we'll plug these in above. So basically we get, and instead of writing Q in minus Q out, this is just the heat transfer, Q12. This equals the mass times a change in the specific internal energy plus the kinetic energy change, so 1/2 mv2 squared minus v1 squared, plus the potential energy change, mg z2 minus z1. And then instead of separately showing work out minus work in, we'll just show this as W12. So this is really just a shorthand. Again, we recognize there may be multiple heat transfers, there may be multiple work terms even. We'll just show it as W12. And within any problem statement, we'll just make sure that we use the right sign and we include all the various heat or work terms. So this equation right here is really what we want. Okay? This equation is our energy balance for a closed system, which we can also call the first law. So this is our first law, or we can call it the energy balance, or often I'll just abbreviate it E balance for energy balance. This is the first law, or E balance, for a closed system. Now, as long as I'm labeling equations, let's just use equation E as our energy balance equation. Okay. Now, I will note that everything we're going to do for any closed system problem from here on out is going to use this equation or some form of it. There are some alternate forms of that, which we'll get to here shortly. But everything we're doing revolves around this particular equation. Okay? This keeps track of everything. It keeps track of what's changing within the system, whether it's internal energy or kinetic or potential energy, and it also keeps track of the energy that's coming in as heat or work through the Q and the W term. So this is our first law. It's really important. Okay, what about these other forms of the equation, and how do we know which one to use? Yes?
Using that, shall we turn it on?
Oh yeah, we're not going to be using this right now. Maybe you could just kind of get rid of that. I wasn't thinking about it, and just kind of replace it with the notes. Thank you. Yeah, again, I want to remind all of you that if I miss something like this, don't wait 20 minutes. Just let me know right away. And often I'm just not even thinking about it. I've never done this before, so. Anyway, hopefully it'll come up soon. So let me just continue, and we can use the board over here to my left for the time being. So what would be some of the other forms? So other forms of the first law. Now, if I wanted to, I could write this in its incremental form. I don't have to write it as an actual equation like this. So in an incremental form, I can write it this way. I can just write delta Q equals du plus, and then here we would have the incremental form of kinetic energy, so that's actually mv dv. And then the incremental form of the potential energy is mg dz. And then we can write the work term as S plus delta W. So I'll just call this one equation F. So this is another version of the same equation. Ooh, now we lost them both. Okay. There we go. Yeah, I don't know what happened to this one over here, but I may do another example problem today, but I'm not sure. It depends how much time we have. So yeah, let's just kind of leave this for the time being. All right, so rarely are we going to actually work in the incremental form. Usually we're going to have a problem where we know the initial state, we know the final state, that is, we know points 1 and 2, and we would just use equation E. However, there is another useful equation even beyond this. So what we want to do is we want to divide equation E by the mass m. And this gives us another form that we're probably more comfortable with. So what happens if we have the total heat transfer divided by the mass? Well, then this is the heat transfer per unit mass, and this would then be lowercase q12. If we divide by the mass, then we have our change in specific internal energy. We have our change in, I guess it would be the specific kinetic energy. So just 1/2 E2 squared minus V1 squared. We have our change in potential energy, GZ2 minus Z1. And then we have the total work per unit mass. So this is lowercase letter W12. So this is just another version. And all we've done is divided out the mass. Maybe we should put some units around here just so we can keep track of things a little bit better. The equation they called E, that would either have the units of kilojoules or BTUs, right? Energy. Heat transfer has units of energy, work has units of energy has units of energy. So it's either kilojoules or BTUs. Down here, in this most recent version of the equation, it's energy per unit mass. So this is going to be either kilojoules per kilogram, or it will be BTUs per pound mass. And again, I suppose I better label it. We'll call this one equation G. So really, it's E and G that are the most common. Look at any example problem, look at any homework problem, and try to determine which version of that equation you want. It really depends on what's being asked for. Some problems you might know the total amount of heat. Other problems you might know the heat per unit mass. Some you might know the total amount of work. Others you might know the work per unit mass. Just read the problems carefully and determine which version, whether it's equation E or equation G of this first law equation, you're going to want to use.
Professor,
Yes?
is that V12 or treble clef 12 or
Where? Here?
to left, like the equals to left and equal?
The Q?
Oh, that's Q.
Yeah, that's a Q one. So lowercase q replaces the capital letter Q, right? Lowercase w replaces the capital letter W. So whenever we've divided by mass, yeah. Okay. Well, another thing to note. I mentioned previously that when we have work, there could be different kinds of work. Often, we would just write W12 as the sum of the boundary work plus any other form of work. Or if we want to, if we have work per unit mass, then we can also have boundary work per unit mass. I mean, anything where there's a total amount of work, we can always divide by mass and get the work per unit mass. For instance, if you look at the equation, the integral of PdV, can we just change that to the mass times the integral of P d lowercase v? So we could always just divide out the mass, but we do recognize that there may be some other forms of work based on stretching of a wire, work based on compression of a spring, work based on electric resistance. So often it's convenient for us not to just leave this as a W12, but just remind ourselves that there are other forms of work besides the boundary work that we may want to consider. By the way, at the end of all this, you're going to be probably somewhat confused. There's going to be all sorts of new equations. And then my intention is to go through just a whole string of example problems that's going to last all of Wednesday and probably all of Friday, maybe even into the following Monday, just to see all the different types of problems that we have. Okay. Anyway, let's move on. We're still talking about the first law for closed systems, but as a side note, let's look at enthalpy. Oops. So enthalpy use. All right, so enthalpy use with the first law. Okay. Now, it turns out that you're typically not going to use enthalpy when solving problems for closed systems. Okay, it's just typically not done, except for one important problem type, which is for constant pressure problems. So enthalpy used in the first law. And this is only going to apply for a constant pressure process only. Okay. Now, why does this deserve something special? All right, let's go back to our first law and we'll see. So I'll just use the basic form, equation E, if you will. All right, so this is going to equal the change in internal energy plus kinetic energy. I mean, just for simplicity, I'm just going to write delta KE and delta PE for potential energy. And then we're going to have our work. Now, we again recognize that the work could be boundary work, or it could be just work based upon some other process. However, okay, picky. No, I'm kidding. Yeah, sorry about that. So we have the internal energy change, and again, kinetic and potential energy change. But what is the boundary work for a constant pressure process? We saw this before, right? We know that the integral of PdV just becomes the pressure times the integral of dV, which is just the pressure times change in volume, right? So it turns out that the boundary work, specifically for a constant pressure process, is pressure times change in volume, or if you will, mass times pressure times change in specific volume. So these are lowercase v's here. And then, again, we'll just write other. And again, these other forms of work could be anything besides boundary work. Okay, anything else. Do you remember the definition of enthalpy? Remember how enthalpy was defined as pressure times change in volume? So can you see that here I've got mass times change in internal energy, and here I have mass times pressure times change in volume? Can't I just combine U2 and P2V2 and call that H2? And can I combine U1 plus P1V1, and isn't that just H1? So I'll just note here, but H equals, by definition, U plus PV. Now note, this is lowercase letter h, so that's why I have a lowercase u and a lowercase v. But h is equal to this. So if we just plug in above, then what do we get? We get heat transfer equals, so I have mass, and let's see, U2 plus PV2 is H2, minus U1 minus P1V1, so that's minus H1, and then plus the change in kinetic and potential energies and the other work. Okay. So this equation is the equation you can now use, but only if you have a constant pressure process. Let me just rewrite that in its complete form by including the kinetic and potential energy. So we have heat transfer, and you know what, I forgot my subscript 1, 2. So Q12 equals M H2 minus H1. And then here, well, this is just our 1/2 M V2 squared minus V1 squared. And then mg z2 minus z1, and then plus the other work. So there's your equation. Now again, this applies only for closed systems, but for constant pressure only. Now, do we have to use this equation if we have a problem that involves the first law? First of all, no, we never want to use this equation unless it's a constant pressure problem. And even if it is a constant pressure problem, you don't have to use this version of the equation. It's your choice, right? You can always go back to equation E or to equation G, just the general forms. It just is a little bit more difficult, right? If we go all the way back to like equation E or G, we're going to need, we're going to need internal energy data, and then for the work term, the boundary work term, we're going to need pressure as well as volume data. So that's 3 different properties. I don't need all that anymore, right? I can get by just using the enthalpy. Instead of internal energy data and pressure data and specific volume data, I can combine them all into one for these constant pressure problems and use only enthalpy data. So it just really simplifies the problem. Again, you don't have to use this equation. It's just there, and it will make the mathematics go a little bit more smoothly. Now, one last thing to note here. Like above, there is another form. I'm not going to show it in its incremental form, but if I just divide by the mass, m, then I get lowercase q12. And this is just going to equal the enthalpy change. And then, again, I just get the mass-specific forms of all the energy terms. And I'll just show this as lowercase w. Okay. So it's the same equation, except everything is now lowercase, and I've gotten rid of the mass terms. All right. Again, you don't have to use either of these last 2 equations. It's really entirely up to you. So any questions? All right. One other thing to note here, and this is kind of a side note. Okay. When you're looking at data tables, like the tables that are in the textbook, everything has to be given with respect to a reference point. Call it a datum or a 0 point, if you will. For instance, we know that pressure is equal to 0 in an absolute vacuum, right? That would be P equals 0. We know that volume equals 0 if the space comes all the way down to nothing, right? We know that temperature equals 0 if we're in the complete absence of matter out in the middle of outer space. Turns out that we have to come up with a 0 reference value for all the other properties too, like internal energy or enthalpy or entropy. Now, this may or may not be clear to you. It depends on how carefully you read through the book. If you were to look in your textbook and read about reference points, you'll see that water has a reference point of U equals 0 as a saturated liquid at 0 degrees Celsius. That's just the reference point. On the other hand, the refrigerants have a value of U equals 0 for a saturated liquid, not at 0 degrees Celsius, but at minus 40 degrees Celsius. That's just where the reference point is. You can look at other tables. For instance, there's some air tables that are in the book, And it uses a reference point for air that's not U equals 0 at 0 Celsius, but U equals 0 at 0 degrees Kelvin. So reference points can be different for every substance in the tables. So that's my side note. Okay. The 0 reference point value varies from substance to substance. Okay. Now, if we are just looking at a pure substance, which is generally all we're ever going to do in this class, then this statement is of no value to us. You know, we're just going to use the data right out of the tables. We don't care what the reference point is. We just have a pure substance. But what if we have a problem like, say, something near the latter part of ME302, which you're not going to get to for quite a few months, where maybe we have a problem that involves two different pure substances, like how about the atmosphere, right? The atmosphere contains air plus water, well, water vapor, right? How do you use your data if the atmospheric air is part water and part air, yet the air tables have a different reference point than do the water tables? That's the point of all of this, okay? The fact is that these reference points vary from substance to substance. If you're solving a problem where you've got two different tables with two different reference points, then you can't use both those sets of data in the same problem. You somehow have to resolve this discrepancy between the reference points. Now, you're never going to have that issue in this class, but 4 months from now, you might have that issue. In fact, you most likely will. So just make a note of that, bury it deep in your mind somewhere. The 0 reference point does vary from substance to substance, and this is a future problem. Future being the key word right now. This is a future problem when dealing with mixtures. Of substances. And you definitely will be talking about mixtures of substances, not just atmospheric air, which is the most basic mixture, but just mixtures of any of a number of other substances. So it's just something that's worth noting. Again, this has nothing to do with what we're doing right now, but this is when it's discussed in your textbook, so I thought I would just discuss it now. Which now brings us back to chapter 1. Why chapter 1? Okay, you might recall that I had mentioned that section 111 talks about problem-solving techniques, and I just thought it was too early to talk about this. Now it's not too early anymore. Now would be a good time to talk about these problem-solving techniques, and it's just going to make your life a lot easier when you're solving problems. So how do we want to approach our problem? Again, I'm going to give you a lot of example problems starting next time. I'm sure I'm not going to have time today. So there's basically 7 steps. And the first step is to state the problem. Now, you can do it any way you want. You can use your own words. You could simply copy the entire problem. It doesn't matter to me. It's really up to you. You know, if you want to reword the problem because you don't like the word vessel and you want to change it to tank, then be my guest, okay? If you don't like the word adiabatic and you like the word no heat transfer, fine, reword the problem and say that there's no heat transfer. But you need to understand the problem, so you need to state it in a way that makes sense to you. But it's the first thing you want to do. Copy it right there on the page. Don't just leave it for the book. 2 months from now when you're studying for the final exam, you don't want to have to rummage through the book for a problem statement, right? So have it on the actual page, okay? You also want to identify the various known information. So you want to identify, let's say, the known properties, or maybe any known states, any information. Any information that you know, you want to identify that right up front. This could be initial conditions, right? This could be final conditions. This could be what substance you're dealing with. This could be the type of system. Is it a container? Is it a piston cylinder device? Is it a bag? Is it a box? Is it a tank? These are all things that you would need to identify as you're beginning this problem. And it's not enough to identify the knowns. You also want to identify the unknowns. Particularly, you want to identify the unknowns of interest. Are you interested in the final pressure? Are you interested in a polytropic exponent? Are you interested in the initial volume? I mean, what is it you're trying to find? So it's not enough to just identify what you do know, but you also want to identify what you don't know that's of interest to you. And then you also want to identify any processes that are involved. Is anything equal 0? Is anything constant? Is temperature constant? Is pressure constant? Are there any dependencies? You know, like pressure and temperature being dependent upon one another in the two-phase region. So you want to do a real good job right up front in identifying the problem. Okay, step number 2 is make a drawing. And here I'll just say draw a schematic. Okay, this is going to be your physical sketch. Okay, so make sure we can see what it looks like. If it's a tank, show a tank. If it's a pump, show a pump. Okay, number 3, state assumptions. Okay, by the way, this is discussed in a lot more detail in that section 111. So what assumptions are there going to be? Are you going to make some assumption about the kinetic energy? Are you going to make some assumption about the potential energy? Are you going to assume that it's an ideal gas? I mean, what is it you can assume? Okay, so you want to make these statements. By the way, when I say KE is 0, PE is 0, that's not uncommon. I mean, if you think about it, if you just have a tank and it's sitting on this desk and it undergoes a process, there's no change in height for that tank. The problem's not going to say the tank remains on the desk. It's just going to say you have a tank. So you assume that there's no potential energy change because the height doesn't change for that tank. Or the speed, right? You've got a tank of water. There's no velocity associated with what's inside that tank. So you can assume that the tank has no motion. You can assume that the material has no motion inside that tank. So make those kind of assumptions. Next, you want to identify whatever equations are appropriate for that particular problem. Okay. You want to identify the first law. Which form of the first law? You want to write down maybe your ideal gas equation of state and the appropriate form of the ideal gas equation of state. Is there some boundary work? You have to write down the boundary work equation. Is it a polytropic process? Do you need to write down polytropic equations? So write down whatever equations are appropriate. Okay. Number 5, identify the tables that are used or equations. So identify where your property data is from. Okay. Is it going to be a particular table? Is it going to be an equation of state? Is there going to be a particular graph or a figure? But you need to identify where your data is going to come from. And it's also a good thing at this point to do like your PV or maybe your TV or some other sketch. Okay? Not to be confused with the physical sketch, this is a thermodynamic sketch, right? This is where you're going to show your pressure volume curve. This is where you're going to have your dome, your saturation, your saturation region. You know, it's good to have a sketch like that so you can kind of move around from one point to another and keep track of what's going on. So you want to do your sketches. And then item number 6, finally, you can do the calculations. Right? You know what equations to use. You know where your data is going to come from. You've stated all your assumptions. You have all your sketches. Now this should be the easy part. The hard part, honestly, is steps 1 through 5, just setting up these dark thermodynamics problems. Once they're set up, the rest is easy. And I'll demonstrate that for you time and time again as I go through example problems. Now, they're not going to be easy for you at first, right? It's going to take time for you to get to be as good as I've learned to be over the years. But if you follow these procedures, it should go a lot more smoothly. Anyway, do the calculations, right? Be careful with your units. Be careful with your significant figures. You know, if you have 3 significant figures in the data, then use 3 significant figures in the solution to the problem. I'll often have students that, you know, will just use every single decimal point on those tables, you know, every number down to the 6th or 8th decimal point. You absolutely don't need that. Okay, and then finally, at the very end, analyze your results. Okay, don't just assume that because you have a number that it's the right number. Does it look okay? Does the number look huge or does it look too tiny? Is the sign correct? Are the units going to be correct? Is the number too big or too small? I mean, you want to look at those results and don't just assume that they're right. Try to analyze them. You know, especially this thing about the sign, right? We know what direction heat transfer and work are supposed to be. So you got to get the right signs there. What kind of conclusions can you draw based on your results? I mean, there was one homework problem where you're asked to find how many air conditioning units could meet a certain demand, and you went through the mathematics, and the answer was something like 1.87. There's no such thing as 87/100ths of an air conditioner unit, right? You don't just go to the store with a big axe and chop off the 87% you need. What conclusions can you draw? Well, I need 2 air conditioners. I need at least 1.7 on paper. I can't buy a fraction of an air conditioner. I got to have 2. So what kind of conclusions can you draw based on your results? So these are the kind of things you want to start thinking about. Anyway, I'm out of time for now. Next time, we'll just jump right in, going through all sorts of example problems of different types using different kinds of data. And this is really the beginning of our thermodynamic analysis. Up until now, it's just discussion of the basic tools you're going to need. Now we go through real thermo. So that's all for today.